Looks freaking awesome.
It's my 11th one.
I think you guys, this looks great. And if you want, I can probably.
I think that wind's gonna mess you up. I think that wind's gonna mess you up. The wind's gonna mess you up and it's gonna throw you off. You're gonna miss.
Does that look better without the little zero lines? What do you think?
Yeah.
We just by the kind of rise out with that. Yeah. For some reason, Excel mathematically pisses me off. When you type 0, it puts a 1 pixel line in, which as a math guy, I'm like, that's not 0, that's 1. Like, don't do that. Yeah, whatever. It's one of my things. These are great. Thank you. What I want to do is talk about them. I want to talk about these. So what you're looking at are called sampling distributions. Those of you taking the 244 journey, this is pretty much all 244 is establishing these things. Randomly sampling from a population that you don't know anything about before you start. Collecting the data, averaging it, and then looking at the results of what you got. Now, do you remember the original populations that you were sampling from? I know it was like 10 minutes ago, but we're going to go back to that again. So here they are, right? Here was blue. Blue had an average of about 8.2. I'm going to bring somebody's on the board, actually. Blue had an average, so blue had an average of 8.2 and a standard deviation about 2.7. Okay, that's blue. Skewed. Yellow, also skewed the other way, had an average of 4.5 and a 2.2 standard deviation. Green had an average dead center 7, yeah? And a pretty wide plus or minus 2.9 because there's so much stuff in the tails there, yeah? Some of the tails. Orange, bimodal, super fun, bimodal, with an average of 7, which is kind of fun to talk about the average being 7 when the modes are nowhere near 7. I kind of like that about it just because it's so freakish. So this is orange. And a plus or minus of 2.2-ish. And then last but not least, red was the only one that looked kind of like a bell curve from at the beginning. And it had an average, it was pretty high, right? It was, 9.2 with a plus or minus of 1.5. Really tight. That's the smallest plus or minus. Hopefully you can see why. Smallest variability, tightest curve. Hopefully that makes sense. Everything's kind of clustered. Good. Please, Zach.
You're calling it skewed even though it's bell-shaped?
It's skewed from 7. It's skewed from, I'm sorry, I'm calling it skewed off of fair. In itself, if you don't compare it to the fair dice, it's not skewed at all. It's perfectly symmetric. Well, it's symmetric-ish enough. But it's the average is skewed to the right compared to the fair dice. Sorry, I'm going back and forth there.
Okay.
Fair enough? Now, here's what you guys got as far as results. Does anything surprise you about your results? Let's do them one at a time. Red. Here's the red one right here. Here's the red sampling distribution right here. Now that looks similar to the original distribution, doesn't it? Okay. Looks similar to it. Let's take red away just for a second. I'll put it back in. There's blue. I'm going to put red back in. So that's the distribution you guys did. Blue. There's blue. Does that look to your original distribution? Does that look similar? What do you think? Okay, so pointing a little to the right there. Skew to the right a little bit. Okay, hold that thought. Let's go with yellow now. Here's yellow. Okay. Okay, that was almost to the left. Okay. And then let's look at green. There's green. Does that look like original distribution?
Kind of.
I'm starting to see some people looking like this now. They're like, wait a minute. And then here's orange. And Rob's like, wait a minute, that doesn't look anything like the original distribution. The original distribution for orange, if you recall, looked like this. But yet your sampling distribution looks like what?
Opposite.
Oh, good! It's almost like it's inside out. That looks like a bell curve, doesn't it?
Yeah.
Original distribution didn't look like a bell curve. Okay, now hang on, let's go back one by one. There's the green, yes? Here's the green here. Okay, good. Different?
Yeah.
You see the look at the here's the original distribution. You got a spike at 12 out here, yeah? You got 12. You got a spike down here at 2. Look at your samples. Look at your samples. Looks like you got 1 out here at 2 and nothing out here at 12. It looks like everything you got fell towards the middle of that distribution, yeah? And we kind of lost the ends of it. Interesting. Here, whoops. Yeah. Here is yellow. Now, as somebody mentioned, yellow is skewed, and here is the original yellow distribution right here. Highly skewed, with a running tail. But look at your sampling distribution of yellow. What do you notice about it?
Doesn't tail off.
We lost that tail on the one side. Now, if in this original distribution right here, you were able to cut the tail off, how would you describe what remains? As roughly. Would you call it roughly a bell shape if you could cut the tail off? So it seems like if you cut the tail off in your sampling distribution, now I say you cut the tail off, you didn't cut anything off, it just cut itself off. Right? And it becomes more of a bell shape. Pretty slick, huh? Pretty slick. And then last but not least, oh, blue, I have to do blue too, sorry. Blue, if you remember blue was this guy.
Yeah.
He had this tail running over on this side and then this triple hump. Well, look at the sampling distribution that you guys got. Where is this triple hump? Well, it's gone. There's a single hump. Where's the single hump? Where's it? The single hump's out there. What's it above? Looks like it's above 7 and 8 here. Yeah, 7 and 8, right? Zach, what are you looking at right now? Your eyes are going left to right. I love that.
I was just comparing.
Good. He's comparing.
29.
Good. I'm gonna do well. That's Control Z with that red one. So it looks like no matter what the original distributions we got looked like, the new ones all kind of look like what? They all kind of look in varying degrees like some kind of bell shape. Now maybe the ones that started more symmetric look more bell shaped now, like red. You guys had red. And yours already was basically bell shaped for starters. So the fact that it looks bell shaped isn't very surprising. But some of them weren't even close to bell shaped in the beginning, and yet we got ones that looked extraordinarily bell-shaped looking at the end. Why do we like bell shapes so much? Give me one reason why we like bell shapes so much. One reason. Besides the fact that I made you study them for like 3 weeks. But what's...
To the standard.
Because we can get them down to a standard normal curve. Why do you like the standard normal curve so much?
Everything's the same. Everything's like...
Good, it's predictable.
Yeah.
You know where the middle is. You know 50% is left of middle, 50% is right of middle, right? What's in the middle? Statistically, we call the middle of a bell curve
Average.
Average, yeah? You see these averages right here? 8.2, 4.5, 7, 7, 9.2. Can you see them in those curves at all? Can you see them in those curves? Let me ask it a different way. If I didn't tell you what the average of this blue one was, would it be challenging to find it? At least quickly.
No,
find
because
it.
you're on a projector and we could still see the numbers.
Excellent. Best answer I've heard all day. Thank you, Omar. Yes. Because your arm doesn't mute the screen. No matter how Italian you are. Well done, sir. Well done. Wait till August. Spend some time outside cutting my lawn. Good answer. So, is it easy to find? Whoops. Oh crap, hang on, so delete, uncut. Is it easy to find where the average is in this bell curve? Fairly, yes? Fairly. It's going to be near where the highest bar comes up. So we know, because we cheated a little bit by counting the population, the average is 8.2. But you could figure that out by looking at this bell curve and figuring out where your pen had to balance the bell curve, yeah? Obviously, it's a little bit to the right of this bar, because of where the weight lies. So you can probably guess that it's somewhere right around here, which is damn close to where the average is. Why is this so exciting? Are you going to be able to do that in the world? Remember how you got this 8.2? What did you have to do? Zach, give me that phrase again. You can approximate that phrase again?
Count all the faces up and add them.
Count all the faces up on the die, turn them in your hands, then calculate it and add them all up and divide by blah. You can't do that in reality. This class isn't called parameters, it's called statistics. What you guys just did is pure statistics. You took a random sample from the population and averaged it a bunch of times. So this is something you actually can get in reality, a sampling distribution. You can't get the parametric distribution in most cases. On a pair of dice, of course you can. But if you're talking about studying ADHD behavior on different kinds of medicines, you can't interview every single ADHD kid. You get a sample of them. You get a sample of them. So you can find the high point of this curve. Looks like it's right about here. You can also find the high point of the yellow curve. Okay, what does it look like? Somewhere in here, maybe a little bit to this side. Now, when you look at the original population, which you'd never be able to do, of course, because it's your population, it's highly skewed, yeah? It's highly skewed. The mode is actually over here, but the average is actually further to this side. The sampling distribution points you right to it. It's almost like giving you a sign saying it's over here. High point of the curve, this is where your center is. No matter how goofy your population is, it's showing you where the center is. Pretty slick, huh? Pretty slick. Let's go back to these samples. Get rid of the yellow again. There's green. Now green in the population, if you could see it, was the flip of the bird distribution. There it is. And the average is pretty obvious there, it's at 7. But again, you wouldn't see this. Could you approximate from the sample roughly where the average is going to be? Where would you balance that curve? Right about here, yeah? Right about here. And get a little drop down there, which is totally fine. You didn't have a whole lot of data. But it's going to be in that middle point, yes? And the same thing goes for orange is one of my favorites. I love the orange one only because it's bimodal. So the original distribution for orange was so freakish. Where is it? There it is. But look where the average is. Look where the average is on that curve. It points you to it. Look at the highest bar. This is where your average most likely is. Pretty slick, huh? So even though you can never get these in reality, you can still get them through sampling. Isn't that rad? I think that's kind of rad. Personal opinion. Personal opinion. How about these? Do you see those anywhere? This is a much harder question. And if you don't see them right now, that's okay. But does anybody see these numbers anywhere in those graphs? Let me put them all back up there. Anybody see them? You can say no, it's totally fine. It's not anywhere near as obvious as the averages.
No, I do not see the thing.
But that's good. This is good. It's totally fine. First of all, there's two problems working against this. Number one, it's very subtle. And number two, they're very close together already, so distinctions are going to be hard to see in a small sample size. So I decided to help us see them a little bit better. I designed a second sheet. Oops, not in Word though. Wrong one. It's down here. So not to ignore every single other group, but I stuck with the blue dice for this one. But please realize that what I'm about to show you would work just as well for the other colors as well. But I just did the blue ones.